This is a video recording for the lesson 6-2, direct and indirect variation. Okay, so again, remember, as we're going through this, you are supposed to be having your workbook out with you, filling in the notes as we go, just like we would normally in class. Okay, so again, this one's focused on direct and indirect variation. All right, and we're going to start off here with this idea that Margot is loading the boat with supplies that she needs for her diving expedition. Each box is 10 inches tall. Okay, so if we were to look at a table or a graph of this showing the number of boxes versus the height of the stack, well, we would start off by saying, okay, obviously if we have no boxes, we have no height of stack. Okay, then for each box we add, we go up by 10 because, again, each box is 10 inches. All right, so if we were to plot that, right, our points would follow up by 10 every time. If we were asked to make a line, we would connect them with a straight line through those points. Okay, so fill that in. All right, number 2, write a function to represent the data in the table above. Okay, so if we're looking at this, we are up by 10 for every box. So it is 10x plus nothing, right? So we could just say 10x is our function of x. And again, remember, function of x, f of x, is also known as y. Okay. Now, number 3, what do f of x or y and x represent in the equation from item 2? Okay, well, x represents the number of boxes, right? Because, again, it's 10 inches per box. And f of x or y represents the height of the stack, or the total height of the stack. Okay, now, this concept here, since these boxes cause an immediate and an obvious impact, okay, this is this thing called directly proportional. Okay, the number of boxes is directly proportional to the height of the stacks. Okay, and what that is here is that in a direct proportion, it's a relationship where the ratio of one quantity to the other remains constant, meaning they both go up or down. Okay, so again, as one goes up, the other one goes up. If one goes down, the other one goes down by this common ratio. Okay, so again, for example, the way we can use this here is to figure out the height of 12 boxes. So again, for example, we said every box is 10 inches, or there's 10 inches per every box. Okay, that's a ratio of 10. Okay, so that would be the same ratio here as if I had 12 boxes. Okay, so essentially we're asking, okay, if I have 12 boxes, what's my total height? Okay, and since this is equal to 10, we could set up a new equation here. 10 is equal to x over 12. Okay, and to isolate x, we multiply by 12 on both sides to cancel those out. 12 times 10, 120. So what that's saying is if we have 12 boxes, the height, or the total height of our stack, is 120 inches. Okay, moving on down here. Okay, again, it's this concept of this thing called directly proportional. Okay, because when they are directly proportional, there's what's called a direct variation. Okay, and in terms of this example here, the stacking boxes and the height of the stack. Okay, and so basically here, the height of the stack varies directly as the number of boxes. Okay, varies directly as the number of boxes, meaning, again, the height is dependent on how many boxes, right? And again, there is a obvious and direct relationship, and that relationship is that each box has 10 inches or represents 10 inches. Okay, so now generalizing it here to number 5, using variables x and y to represent the two values, you could say that y varies directly as x, which means here, okay, the height of the stack, again, varies based on the number of boxes changes. Okay, or another way of saying it is, again, as x goes up, y goes up. So as the number of boxes increase, the height of the stack also increases. Okay, so again, that's what we're saying here with this direct variation, or this directly proportional relationship. Okay, and the direct variation is defined by this equation. Y is equal to k times x, where k just cannot be 0. Okay, k is what's called the constant of variation. Okay, it is a coefficient because it's going to be a number out in front of our variable, and it is going to be constant, meaning that number is not changing. Okay, so the coefficient in our relationship of f of x is equal to 10x, well, our constant of variation is 10. right? We're looking for the coefficient in this, right? So our constant is 10, okay? Why do you think the coefficient is called the constant of variation? Well, obviously because it's the value, it is the constant value by which the other values change or variate, okay? So it is a constant value, right, in this example 10, that changes the other values. Okay, moving on down to number 6. Explain why the value of k cannot be equal to 0. Reason being, if k is equal to 0, okay, then anything times by 0 is going to give you 0. So there's actually going to not be any change in the y value. It would always equal 0 regardless of what x is. Okay, so if we were to rearrange this equation or rewrite this equation to solve for k, right, we would again divide both sides by x to get k by itself, and we get y divided by x equals k. Okay, so we could have our equation this way, or we could see it in this form. Okay, now, next concept here. If we look at the point 0, 0, okay, in the terms of our table and graph here, okay, that is the stack of 0 boxes has a height of 0. Okay, stack of 0 boxes has a height of 0. Okay, and this 0, 0 point is again called the origin. Okay, the origin. Now, this next thought here says the graphs of all direct variation are lines that pass through the point 0, 0, or the origin. Okay, now, this might be a little tricky to think about if you don't put it in terms of an equation. Okay, so if we look at the first version of our direct variation, okay, y is equal to k times x. Okay, well, if x is equal to 0, right, then theoretically, right, y should always be equal to 0. As long as there's a direct variation or a directly proportional relationship, this statement should be true. Okay, because again, if you have x is equal to 0, whatever value k is, it's going to be multiplied by 0, giving you an output value for y of 0. Okay, now, letter C, identify the slope and y-intercept of the graph of our stacking boxes. Okay, well, that's easy, right? In the graph of our stacking boxes, we go up by 10 and over 1, right? Our rise over run, or delta y over delta x. So our slope value is actually 10. All right. Then our y-intercept is this point where the line crosses our y-axis. So if I scroll back up here, right, it's the point where we cross the y-axis. This is our y-axis, so our line actually crosses at this point 0, 0. If our other line, okay, if we were to have a line that looked like this and it crossed at 60, our y-intercept would be at the point 0, 60. Okay, so again, our y-intercept here is at 0, 0. If we were to have a second line that looked like that, it would be at 60, just wherever it crosses that axis, okay, or wherever it intercepts that axis. All right, so if we were to describe the relationship between the constant of variation and the slope, we're going to find out, obviously, they're the same, right? They are equal to each other. They are the same. It is the factor by which we are changing our output values, right? The slope, the rate of change. Okay? So we've now come to our first check your understanding. Okay, so again, you're going to skip these and we are going to go over these in class and work on them together. But if you'd like to look at it, tell whether the graphs, tables, and equations represent direct variations. Okay, so now we're going to check our understanding when we get back to class. Now on this next one, it says, Hoonan is stacking identical boxes on a pallet. The table below shows the height from the floor to the top of the boxes. Okay, so if we were to try to draw a picture of what this looks like here, okay, we have some pallet and we are stacking boxes on top of the pallet. Okay, and again, the boxes are going to change the height. Okay, but we do have to account for the height of a pallet. Okay, so the height of this pallet here. Okay, so if we look at this here, we have to kind of understand, right, what is our rate of change here? Okay, so going from 2 to 5 is going up by 3, okay? And my height or my output value, right, is got to change in 15. So if I want to figure out what's the constant rate of change or my slope, or again, I'm talking about boxes, right? Because that's what I'm adding. That's my change, okay? I can figure out those numbers by doing, again, the change in y, which is my height, over the change in x, which is my number of boxes. So 15 over 3 gives me a value of 5. So what does that mean in the context of this problem? That means that each box is actually 5 inches, okay? So then we have to look and we say, okay, but if I have 2 boxes, right, 2 times 5 is only 10. And the actual height here is 16 inches. So where do those other 6 inches come from? Oh, well, that comes from the pallet, right? That pallet still has a height to it, okay? So again, if we were to check these other ones, we could plug in a 5, right? And add in this extra 6 inches, right? Would be coming from our pallet. All right? So scrolling on down here, if we were asked to make a graph of the data, right, we could look directly above and plot those points, right, relatively where they are. Okay, and then if I were asked to connect a line, right, we would go all the way through our y-intercept, right, and it would be a generalized line here. So if I had to write an equation that gives the height of the stack and the number of boxes, including the pallet, right, height is equal to 5 times the number of boxes, because each box is 5 inches tall, plus the 6 inches that doesn't change from the height of the pallet. Okay, so again, that's where this equation comes from. In number 11, does the function represent a direct variation? Well, if we looked at the graph here, the answer is going to be no, right? Because it does not pass through that origin of 0, 0. Or if we looked at this equation here, that does not match our y equals kx form. This is actually y equals kx plus some constant. Okay, so no, it does not perfectly match, which means this is not a direct variation. Okay, for number 12, use the equation to find the height of the stack of 16 boxes, including the height of the pallet. So really what that's saying here is that x is equal to 16. So we're going to plug in x equals 16, and we get 5 times 16 plus 6 gets us 86 inches for the total height of that stack, with the pallet's height included. Okay, so we now come to our second check your understanding. Okay, you're going to skip those questions. Again, we're going to tackle those in class. All right. Now, moving on down here, Margot is loading the supplies she'll need for her experiments. All of the boxes have a volume of 400 cubic inches and a height of 10 inches. The lengths and widths will also vary. Okay, so we're talking about exploring lengths and widths. So what we need to do here is come over to the side and look at this math tip. Okay, so I don't expect you to know this equation off the top of your head. If you do, awesome. If not, not a big deal. But volume is equal to length times width times height. Okay? Now, length is going to vary. I'm sorry. Our length is going to vary. Okay? And our width is also going to vary. Okay? But what doesn't vary... Oh, did I put that as an L? I'm sorry. That should have been an H. Is our volume and our height. Okay, those were given to us in the problem. So our volume is constant of 400. And our height is a constant of 10. Okay, so what we want to do here is we want to rearrange this equation here to put L and W on opposite sides, since those are going to vary. Right? And since we know our width value... right? That'll be our input. That'll be our essentially X value here. So what I want to do here is I got to get L by itself over here. That's my output value. That's essentially my Y. Okay, so I'm going to divide by those constants so those guys cross out and come to the other side. Then, since I know that V is 400 and H is 10, I can plug those in and actually simplify. So that turns this into 40 over W is equal to L. Right? 40 over W is equal to L. All right, so that's my equation here that I will use to solve for these missing numbers here. So again, when width is equal to 1, 40 divided by 1 is 40. When width is equal to 2, 40 divided by 2 equals 20. Okay, so when you have a 5, it's an 8. An 8, it's a 5. A 10, it's a 4. And 20 is a 2. Okay, and again, all because we know these two constants there. Right, so our relationship between width and length have to multiply together to get us 40. Okay, then from there, if I take these data points and plot them in their respective locations on my graph here, I'll notice, right, it is decreasing, but it's decreasing at kind of a curve shape here. Okay, at a curve shape. All right, so then number 15. How do the lengths and widths in item 14 relate? Well, we said, okay, if we have this relationship of 40 divided by W is equal to L, that means L times W is equal to 40. Okay, L times W is equal to 40. Or, since length is equal to Y and width is equal to X, Y times X is equal to 40. Okay, so if we use the equation that we wrote up here, okay, we can write a function. Now remember, function notation, right, is f of x, which is essentially y. So right now, in this form, we do not have y by itself. So how do we get it by itself? We divide by x. So y is equal to 40 over x, just like we had above, or f of x is equal to 40 over x. All right? Now, the pattern that we see in the table and the graph, well, is that we see that as the width goes up, the length goes down. Right, so as width goes up, length goes down. Okay. Now, in terms of box dimensions, okay, this relationship shown above, the one up, one down, is what we call an indirect variation, oftentimes referred to as inverse. Okay, oftentimes known as inverse. So, if this is the equation, right, for a direct variation, this is the equation for our indirect variation, okay? Above, our k value was just 40, okay? And again, what does this mean? This means that as x goes up, I'm going to divide by a bigger number. So if I'm dividing a constant by a bigger number, that means my output value is going to go down, okay? Versus if x goes down, right, if this gets really small, right, I'm now dividing by a smaller number, which means my output value is going to get bigger or go up. Okay, so this one up, one down is this indirect relationship or indirect variation. Okay, now letter B, are there limitations? Well, of course, there's always limitations, right? First off, k can't be equal to 0 because if it is, 0 divided by anything is going to give us a y value of 0. Okay, so that can't happen. Also, x can't be 0 because if anything is divided by 0, it's an undefined function, right? There's an error. You cannot divide by 0. Okay, and since neither k or x can be equal to 0, right, because it would make the function untrue, well, I then can't have an output value ever of 0. Can get really close, but we can never actually be 0. Because unless you have the number 0 being multiplied or divided, right, we will not be able to get it in some form. Okay, so moving on down here to letter C, write the equation for finding the constant of variation by solving for k. So again, rearrange for k. Y is equal to k times x, so I need to get k by itself, so multiply both sides by x. X times y or y times x is equal to k. All right, so how does this compare between the direct equation and the indirect equation? Well, they both use the exact same variables, but in this direct relationship, okay, there's division, okay, and in this one, it is multiplication, okay, one's division and one is multiplication. Okay, how do the graphs compare? In a direct relationship, right, it passes through the origin, and as x increases, y increases by that constant value of k. On the flip side, this indirect relationship, as x increases, y actually decreases, because now we have the constant being divided by x, right? We're dividing the same number by a larger and larger number, okay, which is making this increasingly small. All right? So that is where we're going to end, right? Again, we're going to cover the check your understanding in the lesson 6-2 practice in class. So if you have any questions, let me know. Otherwise, thank you.